Okay, should be recording now. Okay, cool. Okay, so this is just going to be like a summary of Kaplan General Chemistry's chapters 1 to 4. So actually, we'll just be doing chapters 1 to 3 today since it actually got kind of long. But if we have time, we will do some chapter 4 stuff as well. Okay, so chapter 1 is atomic structure. It's actually not high yield at all. It's only like 6%, but like the topics in this chapter are pretty important, just as foundations for like the rest of general chemistry. So it is important to understand this. So firstly, I think this is something that everybody knows, like protons are like positive. They're just like +1. E is the fundamental unit of charge. I don't think it's super important, like exactly how much it is, just that it's the charge of a proton, basically. And the charge of a proton is 1 atomic mass unit. This comes from the carbon-12 atom. Yeah, so protons are also the unique identifiers for elements. So each element has a different proton number. Neutrons have no charge, and they weigh approximately the same as a proton. Yeah, so mass numbers are just protons plus neutrons. Isotopes are just like different numbers of neutrons, which means like different mass numbers, but they're still the same element. Because remember, protons are the unique identifiers for elements. So it doesn't matter how many neutrons it has, as long as it has the same number of protons, it will be the same element. And so this actually becomes a more important concept when we start talking about atomic decay. But this is in like the later chapters, so it's not that important yet. So electrons, obviously, it's like a negative -1 charge. The mass is negligible, so it doesn't count for the mass number. It does have a mass, but like it's so small that it doesn't really matter. So electrons are actually like what determine the reactivity, and specific the valence electrons, which are the electrons in the electron shell that's the farthest from the nucleus. And the closer to the nucleus, the lower the energy. So this is important because the closer the electrons are to the nucleus, the more stable they are. And gaining or losing electrons, those are just like anions and cations respectively. Okay, so here are some problems. So what is the atomic number and mass number of C13, and how many electrons does it have? So, and then what is the atomic number and mass number of the oxygen anion? So that's just O2 minus. And how many electrons does it have? So you guys can like, I'm not sure like how you guys want to do these questions. Like, do you guys just want to like answer them in the chat, or like just say them out loud? Or if you want, you guys can just do them yourselves, and then I can just move on to the next slide, which has the answer. So whichever one is like best for you, like just like let me know. Okay. Okay. So I guess like we'll just spend a couple seconds in case anybody still needs some more time, and then we'll just go to the answer. Okay. So Faith gave her answer, and yeah, you're right. For question 1, the atomic number is 6 because carbon has 6 protons, and the mass number is 13 because it has 6 protons and 7 neutrons. And the number of electrons is 6 because it's a neutral element. So great job, Faith. So for the second one, the atomic number is 8 because oxygen has 8 protons, like that's like its element identifier. The mass number is also 8 because it has 8 neutrons. So 8 plus 8, that's 16. And it has 10 electrons because it's an anion. So it actually has a -2 charge. And so to get that, we have to have 2 more electrons and protons. Okay, so atomic mass versus atomic weight. Oh, sorry, I just have a comment. Yeah, the mass number, yeah, so the mass number is actually 16. You're right. I put a typo there. Sorry. Yeah, so thank you, Faith. I'll fix that before I share these slides with you guys. So the atomic mass and the atomic weight are like similar concepts, but they do have like some important differences that are really important to remember for the MCAT, because the MCAT can sometimes like try to trip you up about this. And so the atomic mass is just basically the number of protons plus the number of neutrons. And so it's what varies between isotopes. And so different isotopes have different neutrons. And so they have different atomic masses. But because they have the same number of protons and the same number of electrons, they actually have similar chemical properties. On the other hand, the atomic weight is basically the average of the atomic masses. So elements can occur in nature in like different forms, so in different isotopes. Like for example, like carbon-12 is the most common type of carbon. It occurs like 99.7% of the time. However, carbon-13 is also an isotope of carbon that does occur in nature, very, very little, just like 0.3% maybe. But it does have an impact on carbon's atomic weight. So if you look at the periodic table, you'll find that carbon's atomic weight is slightly more than 12. And so other elements that have like more abundant isotopes have like more impact on their atomic weight. And so that's actually why, like on the periodic table, the atomic weights that you get are like, for example, like 16.2 or like they have decimal places. It's because like they're averages of the atomic masses of different isotopes. So atomic weights are important in terms for moles especially. And so basically, if you have like a certain number of atoms, so 1 mole is 6.02 times 10 to the 23 atoms, then you're going to have like just like probabilistically, like a combination of different isotopes. Like for example, out of that number, like 99.7% of carbon atoms will be carbon-12, but 0.3% will be carbon-13. And so it's important to take that into account when performing calculations. Okay, so here's a problem. So this is just like atomic weight problem. So you have an element that is present has a mass number of 12 75% of the time and a mass number of 11 25% of the time. And so what would the atomic weight be on the periodic table? So I'll just give you guys like a couple seconds just to answer that. It shouldn't take too long. And then you can either like write your answer in the chat if that's what you guys are comfortable with, or we can just like go over the answer. Or yeah, writing on the screen is awesome too. That's perfectly fine. Okay, so let's like go over the answer then. And so this is just like a simple proportions problem. And so if the element is available um, with a mass number of 12, 75% of the time, all you have to do, and then as 11, 25% of the time, then all you have to do is, yeah, what Ginny said. Basically, just put that into the equation and put the percentages um, in their number form. So like 0.75 and 0.25. And so if you put that into a calculator, you should get 11.75 AMU. And if you wanted to put that into moles, then that would be 11.75 grams. Okay, so the next section was on Rutherford, Planck, and Bohr. So Rutherford didn't really have like, they only talked about Rutherford for like 2 sentences, but like he basically discovered like electrons and how they move. And there's actually more stuff about what Rutherford did in like a later chapter. So we'll talk about him more then. But Planck is pretty important because he found the energy of a quantum equals E equals HF, and E equals Planck's constant, which is like that pretty long number. But I highly recommend you memorize this number because the MCAT does not give equation sheets. And then F is just the frequency of the radiation. Okay, so this chapter is actually mostly about Bohr. So Bohr's model is what you probably learned in like high school chemistry. So the hydrogen atom has a central proton with an electron traveling around in a circular orbit, like kind of like a solar system. And so this model is actually like wrong for every other element except for hydrogen. But Bohr did find some extremely important things about elements that are like very applicable to what we know today. So basically, the angular momentum of a hydrogen electron equals L is just like what is denoted as angular momentum, and that is nh over 2 pi. And so n is the principal quantum number, and this is just like the energy shell of the electron. And we'll go over what principal quantum numbers are like in the next few slides. And the energy of an electron is minus RH over n squared. So RH is just Rydberg's unit of energy. And so it's that really long number. I would recommend memorizing this one too, because in a practice test I took, I did have to do a calculation that involved this, but actually like for most MCAT questions, like 99.9%, like what they're looking for is not like exact answers, but like the proportions. So like what I mean is that like for example, for the angular momentum equation, like you don't have to remember like what exactly Planck's constant is, or like, well, I mean, you should probably know pi. So it's just Planck's constant for this one. So, but if you were to say that an electron was in the first electron shell, so n equals 1, versus an electron in like the fourth shell, so n equals 4. So you would basically know just from this equation that the angular momentum of the electron in the fourth energy shell should be higher, because it's a direct relationship between angular momentum and the principal quantum level. And yeah, Faith, pi is 22 over 7. That is an approximation. It's like actually like an irrational number, so it never ends. But like, I guess all we need to know is 22 over 7, or like more commonly, 3.14. In almost like every single equation you do, like 3.14 is going to be completely fine for pi. Okay, so what else can we find out from Bohr's equations? It's that energy increases farther from the nucleus. So if you look at this equation, this actually is not intuitive at all. Like when I was learning this in chemistry, I did have a hard time like figuring out like this number becomes bigger if I decrease the principal quantum number, or like the energy shell. But actually, what they want you to see here is that the energy becomes less negative. So that means that it increases farther from the nucleus. So this will become like more apparent in the problem that we're going to do after this. But just like keep this equation in mind, and keep in mind that it is not intuitive, and that if it looks bigger, it is actually the energy is actually becoming smaller because it's becoming more negative. Okay, so what else? So ground state is just electrons at the lowest energy level possible. An excited state is when an electron has jumped to like a higher energy orbital. So basically electrons always want to be like at like the least energy state possible. And so this is like a concept that we'll talk about in like a later chapter a bit more. But this is just like a law of the universe. Everything wants to be at the lowest energy state possible. In the MCAT, they will just assume, unless they specifically tell you, just assume that everything is in its ground state, unless they tell you that it's in an excited state. Okay, So as I mentioned before, Bohr's model is actually wrong, and electrons are actually localized in space instead of in specific pathways. And so we'll talk more about what this means. So basically it just means that electrons are not like planets that orbit around a nucleus. It's more like they exist kind of like in clouds around like a nucleus. And so they're somewhere in that space, but like we're never sure like where exactly they are. And we know for a fact they don't travel like in a circular path. Okay, so this is just a problem just to bring home the equation, like Bohr's equation. So what are the energies of hydrogen atom electrons in the fourth energy level versus the second energy level, and which one is higher? And so you should be able to answer like the second part of the question, just like based on conceptual information. But it is important to like understand like why and the equation works as it does. So that's why I think it is important just to like see it in action. And so these are the equations. So just like whichever one you think is the right equation, just use that, and I'll give you guys like a minute and then we'll just go over it together. Okay, I think that's about a minute now. Okay, so as you guys probably guessed, we just used the minus Rydberg's constant over n squared. So in like conceptually, like when you see this question, like you should immediately know that the electron in the fourth energy level is at a higher energy because it's like farther from the nucleus. And so because it's farther from the nucleus, that just means like it has like less attractive force to the nucleus, which means like it's more volatile and it's less stable. So just conceptually, and you should know that. But if you do use the equation, then you will find out that although it looks like the answer for the fourth energy level like should be lower, it is actually higher because 1.3 minus 1.36 is like less negative than minus 5.45. So if you ever have to like do this equation, just like keep that in mind because it did trip me up like a lot when I took like chemistry in my first year. Okay. So Bohr's model had like some really important applications that we still use today. And so the main application are the atomic emission and absorption spectra. And so these are also unique to the element because like each element has different like energy level transitions. Sorry. Oh, yeah. So Faith asked like any tips to calculating without a calculator for the last question. And so here, this would be one of the questions, like they wouldn't ask you to calculate this like just like that, but this would be one of the questions that they would like give you as a proportion, basically. And so here's like how you would do it if you saw this exact question or like this was like part of a bigger question. So basically, like you can see that the fourth energy level, n squared equals 16 versus the second energy level, 2 squared equals 4. And so you could just like look at this. Like you don't even need to know Rydberg's constant. Like say like you just ignore Rydberg's constant. Just say it's like 1 over 16 versus 1 over 4. So like negative 1 over 16 is like less negative. So you would just say that that would be higher. in energy. And so like in questions like these, like this is like almost impossible to do without a calculator. Like I'm sure like some geniuses can manage it, but like just like think about it in terms of proportions. Like there's only one unknown here, and that's n. Well, I mean it's not unknown. Like there's only one variable here, and that's n. And so you can just like forget about Rydberg's constant and just do like negative 1 over 16 versus negative 1 over 4. And negative 1 over 16 is less negative. And so that's how you would know that the energy level is higher. Okay. Yeah, thanks for bringing that up, Faith. That's like such an important part of MCAT calculations. Okay. So we'll just talk really briefly about the atomic emission spectra. I don't know, like, I've never had like a question like this. I haven't had a question on this, like, on either like UWorld or on like a practice test yet, but like it could happen. So we'll just talk about it briefly. So we probably don't need to know like the exact names of the electron transmissions, like the Lyman series versus the Balmer series versus the Paschen series. But I would say just kind of know that the Lyman series basically take into account like all of the electron transmissions of like, so like it goes all the way from like the highest energy level to n equals 1, which is the lowest. And then the Balmer is just like 1 less than that. And the Paschen series is just 1 less than that. But yeah, so I think that's pretty much all we would need to know about that. So the atomic emission spectra is basically just like when an electron is excited to like a higher energy level, like it always wants to return to like a lower energy level. So the way so basically like when it does that, it emits a photon. So it emits energy because it's like, because if it's going from a higher to a lower energy level, it's like, it's going to a lower energy level. So it like loses the rest of that energy. And so it's emitted as photon, which is light. And we can just find the speed, we can just find the energy of that photon using, we can just using Planck's equation or a derivative of Planck's equation. And then, yeah, so by measuring like the specific photon frequencies, we can just find the energy of the emitted photon, which is just, which derived from E equals hc or over wavelength. And in combination with this equation, we can find the energy of an emitted photon, and it's just this equation here. And so the atomic absorption spectra is the opposite. It's just like ground state to excited state. So it actually like absorbs energy. And the emission spectrum and the absorption spectrum is like basically the same as the emission spectrum because it's like the same changes in energy levels, just like opposite. So this would actually be like another question that's like, sorry, this would be another question that would be like a proportional kind of question. Because it's like really hard to do without a calculator. But I do think it's important just to like understand it conceptually, to just to do it. So I'll just give you guys like a minute and then we'll like go over it together. And here are the equations. Okay, So that should be like about a minute. And so this is the answer. And so, yeah, so if you just like plug the numbers into the equation, like plug the principal energy levels into the equation, like you will get the energy change. But of course, like if you're actually doing this on the MCAT, like you can forget about Rydberg's constant and just like look at 1/16 plus 1/4. And so you will get, and that's probably enough to like answer like whatever question you're working on the MCAT. But I would like recommend memorizing Rydberg's constant and this equation because it's important to like know this relationship because um, energy questions are like pretty common in the chemistry section.
Quick question. So
Yeah,
if you
sure.
were to answer this conceptually, what would be the answer? Like, is it going for is it a high energy was emitted or a low energy was emitted?
Okay, yeah, sure. So n equals 4 is like a higher energy level, and n equals 2 is a lower energy level. So you're going from a higher to a lower energy, so that emits energy as a photon, because the electron is going to a more stable state. The more energy there is, the more unstable it is. So if you like looked on this question and you wanted to answer it conceptually, like you would immediately know that it was emitting energy because it's going to a lower energy state.
How would the options look like in MCAT? Like, say this was a question, how would you know to pick 6.8? Let's say you don't remember the equation or you just can't do the calculation and you're just trying to answer it based on what you already know. Like, what would the options be? Would they be all negative and get confuse you, or
I would say that the options would more be something like, um, yeah, so basically like this would be part of like most commonly would be part of like a larger passage question. And so you would probably see like answers like, so you can see like this is like negative 6.8 times 10 to the negative 19. So you would probably see like answers like that are positive, which doesn't make sense because these are like electrons that are changing in energy level. And you know that in this equation there's like a negative. So whatever answer you get has to be negative. So you might get like positive. You might get like positive answer choices. Or like for example, like if you try to conceptually do this question, like say like the electron is going from energy level 4 to energy level 2. Like you can just look at this as like 1/16 plus 1/4. Just forget about Rydberg's constant. And then you can kind of like get a ballpark of like what this could be because when you look, when you like, you can just like get a ballpark, and so you might get like answers that are like really different, and so you could also cross those out. But if you did like, but like another way would be to look at like the scientific notation of the numbers. And so like Rydberg's constant is 10 to the negative 18. And then it's like 1/16 plus 1/4. Like if you put that into like scientific notation, it should be like, it could be like 10 to the -1. And so that's how they got to like 10 to the negative 19 in the answer. And so like if the scientific notation of the numbers is like 10 to the negative 10 or like 10 to the negative like 7, then you would also immediately know that that was wrong.
okay. And one last thing, the equation in the book says one. It should be a minus instead of a plus in here.
Oh wait, let me check. Okay, yeah, I might have made a typo then. I should definitely check that. Oh yeah, it is supposed to be a minus. The answer should be right. I think I just like made a typo in this. Thank you so much. I'll fix that before I send you guys the slides.
Okay, no problem. Thanks.
Okay. So the last section of this chapter is just the quantum mechanical model. You only need to like know this like on a very basic level. And the most important part is just the Heisenberg uncertainty principle. It is important to simultaneously determine the momentum and position of an electron. What all that means is that like if an electron is moving, then you can't know like where exactly it is. And if you're trying to find, and if you like know the electron's position, then you don't know how fast it's moving, that's basically all that means. So quantum numbers are pretty important. So the Pauli exclusion principle is just that no electrons can possess the same set of quantum numbers. So you don't need to like memorize this guy's name or like the name of this principle. Just like know that electrons have to have in one element have different sets of quantum numbers. So the principal quantum number is the energy level shell, like we were using in Bohr's equations. It's just like what energy level the electron is in. And it can be like any positive integer. Like the lowest energy level is n equals 1. And then it can go then like on the periodic table, I think it goes to n equals 7 as the highest energy level. And then the maximum number of energy levels is just, the maximum number of electrons is just like 2n squared. So you can just like plug in n, and then you will get the number of electrons. So the larger they are, the more energy, and this makes sense because the higher the energy level is, the farther it is from the nucleus. So the more unstable it is, and the more energy it has. And just remember that electrons always want to be in a lower energy state. So the azimuthal number is depends on the principal quantum number, and it is just like the subshells. And so you might know them better as S and P and D and F, but that's just the azimuthal quantum numbers. And it just goes from 0 to n minus 1, but an easier way to remember this is just that n is the number of subshells. So n equals 2, that means there's 2 subshells. And you can just find the number of electrons by plugging it into this equation. The magnetic quantum number is just minus L to plus L, and it is the orbital. So yeah, so you guys probably know it better as like S, like for example, like if you do like the S orbital, for example, or the S subshell, so it can have like 2 orbitals. So it has like 2 places for electrons to be. And then the p orbital has like 3 places for the electron to be. Oh, sorry, the p subshell has 3 orbitals, which is like 3 places where electrons can like exist. And the last one is the spin quantum number, and this is like the easiest. It's just like plus 1/2, minus 1/2. And 2 electrons in the same orbital have to have opposite spins. So let me just see if I can just like write it here, because I think I probably confused you guys a bit with like the explanation for the magnetic and spin quantum numbers. And so I'll just like write it here. Okay, so this is S. Or sorry. Okay. S is just 1. And this is because like S is n equals 1. And so the number of subshells is just 1. And so the magnetic, and so the orbitals is just like 1 to minus 1. So this would just, if you wanted to put electrons in, then it's just like this. Oh my God. Let me just try to figure this out. Okay. And so these are the electrons with opposite spins. This is an orbital. And then P, that would be the subshell. And then there would be 3 orbitals. And you can put 6 electrons in, like that. Okay, just imagine that these are like good arrows. They're really bad. Okay. Yeah, I would have preferred to do this on my iPad, but apparently it didn't work. So it's okay. Yeah, so that's basically like what it is. I'll just erase that. Okay, yeah. So electron configuration is like a really important concept to know. It's just the off-by principle is just it fills from lower to higher energy subshells, and each subshell has to fill completely. And so you can just like see it from this diagram here. But it is like pretty intuitive. Like if you look at the periodic table, like you can literally just like look at it and go, okay, hydrogen. This is 1s1 because there's 1 electron in hydrogen. Then you would go to helium. This would be 1s2. And then you would just go to the next one. And then it would be, I think it's like lithium or something. And then it would just be 1s2 and then 2s1. And that's lithium. And so you could just like keep on going like that. But what is important is that like sometimes you'll be asked like which subshell would have like lower energy, and then all you have to do would just be like if the n is high, if the n is like lower, then that is the lower energy. If the n's are the same, then it depends on like the L, like if it's S or P or D. And then all you have to do is look at that. And then it gets like really long, like the electron configurations for the elements get really long as you go on the periodic table. So you can just like abbreviate it with the noble gas configuration or the noble gas notation. And that's basically just like using whatever noble gas is like right behind that element and just using that and then like continuing with your electron configuration. And so an example is here, like with the exception. So like chromium, the closest noble gas is argon. And so if you keep on going, you would just go 4s1, 3d5, and this is an exception actually, but let's just go back for a second. Hund's rule is that within each subshell, the maximum number of half-filled orbitals with parallel spins due to electron repulsion. And so basically all Hund's rule means is that like, let me just draw it. So say you have like a p orbital here. And so you have 5 electrons. So you go 1, then you go 2, then you go 3, then you go 4, and then you go 5. What you don't do is go 1, 2, 3, 4. Oh, shoot. Sorry, I actually drew it with the wrong spins. So it actually should be like this. Sorry. It's just really hard to draw on this. But yeah. So yeah, this procedure is what you should not do. This is right. Okay. Okay, but there are exceptions to this, and it is in the transition elements. And so because the half-filled and fully filled orbitals have more stability, chromium and copper actually don't follow the rule to fill like each subshell before you fill the full orbital. So basically, like if you draw this out, what this means is that like this would be the 4s, and this would be the d orbitals, and d has 5. And so for chromium, you would have 4s1, then okay, like that. And so the reason is because that this is more stable than this. And so because they want that subshell fully filled, that's why chromium is an exception. And the same thing is for copper. Like if you just like add the rest of the spins, that's the same logic for copper. Okay. Okay. So let's just like do these problems on the electron configurations of carbon and osmium. Oh shoot, sorry. I'm not sure. Like, okay, yeah. So these are just the answers. And so carbon would be 1s2, 2s2, 2p4. And this makes sense because the 4 valence electrons are in the p shell. And then the noble gas configuration for osmium would be xenon 6s2, 4f1, 4f14, 5d6. And so if you just like go through the periodic table, like that's what you would get. And so the last thing to know for the quantum mechanical model is just the difference between paramagnetic and diamagnetic. So paramagnetic is like when there's unpaired electrons. And so if there's unpaired electrons, if they're in the presence of a magnetic field, they actually like all switch the same spin. And so they become like weakly attracted to the magnet. And diamagnetic means if there's only paired electrons, they are slightly repelled because they don't change their spins to go towards the magnetic field. And as you guys know, valence electrons are the outermost energy shell, and they're the most important for chemical behavior. So this is chapter 2, the periodic table. So this chapter is like really short. It's like, I think like 4 slides maybe. But it is like really important just for like conceptual information. So this is the periodic table. I think everybody is familiar with this. Periods is rows, groups is columns. Columns have the same number of valence electrons, so they have similar properties. The types of elements are just metals, which are lustrous, malleable, ductile. They have high melting points and density, low effective nuclear charge, low electronegativity, large atomic radius, small ionic radius, low ionization energy, and low electron affinity. We'll be talking about these like last few points in like the next slide, so just don't worry too much about them. Nonmetals are brittle, and metalloids are in between. And so for these, you don't have to like memorize them, just like know their general characteristics. But like once you know like the basic properties of elements, then you should be able to figure this stuff out. Okay, so firstly, effective nuclear charge is just like the nuclear charge which is positive felt by the valence electrons. Like just based on magnetism, negative electrons are attracted to the positive nucleus. And so that just means that if there's a bigger nucleus, that means there's more charge, more positive charge. And so that just means that effective nuclear charge increases from left to right. Because as you go from left to right on a periodic table, it just like increases in protons. So if it increases in protons, then so if it increases in protons, then that means that it's more positive, so it has more attractive force. However, if you go down a group, effective nuclear charge is actually constant. And that's because like as you go down, even though the number of protons might be increasing, the number of electrons are also increasing. And so the negative charge of the electrons actually cancels out the positive charge of the nucleus. And so effective nuclear charge is constant in a group. So atomic radius is just how big the atom is, and so it decreases from left to right. And this is because like as you go from left to right, the atoms increase in protons. And so if it increases in protons, that means there's more positive charge. That means there's more attraction. And so it brings it in. Like the nucleus attracts the electrons. And so that's why atomic radius decreases from left to right. It increases down a group, and that's because as you go down, we actually increase in the number of electrons. And so if we increase in the number of electrons, that means the valence electrons are even further from the nucleus. Ionic radius is a bit more confusing, and this is because metals tend to lose electrons while nonmetals tend to gain electrons. So like just imagine, just think about this. Like say you have an atom, then you take an electron away. That means that the radius is going to decrease. And so that's just what happens with metals. And for nonmetals, if you like just take like an element, then you add electrons, then like it's obviously going to increase. And that's just how you should think about ionic radius. So ionization energy is the amount of energy it takes to remove an electron, and this is an endothermic process because it takes energy to do this. And so the reason it increases from left to right is because it's harder to take electrons away because the protons, as you go from left to right, are exerting a stronger charge on the electrons. And so that's why it's harder to remove the electron. It also decreases down the group because as you go down, there's like more electrons separating the valence from the nucleus. And so it's easier to take away those valence electrons. There's also multiple ionization energies because you can remove like multiple electrons. But like as it gets harder to remove electrons, the higher the ionization energy gets. and it gets the hardest, like if you get the element to an octet. If the element is in an octet, like in a noble gas configuration, then like the ionization energy basically shoots up. And then after that is electron affinity, and that's the opposite of ionization energy, and it's to acquire electrons. And so this also increases left to right. And so it increases left to right because of effective nuclear charge. Just because the protons, there are more protons, that means that they want more electrons. They're more attractive. And so that's why it increases left to right. It also decreases down a group because there's more electrons. So it's farther from the nucleus. And so the last one is electronegativity, and that's just the attractive force an atom will exert on another atom. And that also increases left to right because the more protons there are, the more attractive force it has. And so this one also decreases down a group because, as I was saying, because there's more electrons, so it's further from the nucleus. So as you look at this, you can just figure all of this out basically from just like knowing what the trend for effective nuclear charge is. So it's more charge, more attraction. And you can just figure the rest of this out for that. So you don't have to like memorize it if like, because there's already so much stuff you have to memorize. But just like keep in mind, like just as a point, all of these have the exact same trend except for atomic radius, which decreases from left to right. Okay. So here are some problems. I'll just give you guys like a minute to do them, and then we'll just go over it. Okay, I'm just gonna like guess that everybody's done now. I'm not sure like how long this will take, but it shouldn't take too long. Okay, so if you just like look at a periodic table for these, like oxygen has a higher ionization energy because it has like more protons than lithium, but lithium has a higher atomic radius because it has like less protons to exert an attractive charge on the electrons. And so oxygen has a higher electronegativity, again, because more protons, higher electron affinity, also more protons, more attraction, and higher effective nuclear charge, also because of more protons. And so for the second one, you can just do the exact same thing. Just look at the periodic table. And just based on this, you can see that germanium has a higher ionization energy, electronegativity, electron affinity, and effective nuclear force. But calcium would have a higher atomic radius because it has less protons, and so it has less attractive force. The last one might have tripped you guys up a little bit, but hopefully not. So neon has a high ionization energy because it's extremely hard to take electrons away from noble gases. Chlorine has a higher atomic radius, less electrons, but chlorine is actually more electronegative than neon because neon is a noble gas. And so it has like negligible electronegativity. And so the same thing, because neon is a noble gas, it's already in an octet, it doesn't want any more electrons. So that's why chlorine has a higher electron affinity. And this is just a summary on like the chemistry of group section. Like this stuff isn't like super duper important, but I would say like just go over this. Just like know the general trends. A lot of this is like stuff we already said, like it's just a summary of that. Okay, but like one thing I do think it's important to know is just like color perception, because I have had some questions on the MCAT about this. And so this can be tricky because like our brain actually doesn't use like the type of like color processing as paint. What we see is like subtractive processing of light. So what I mean is that like when we see color, what we're basically seeing is like light being reflected off a surface. But when light is being reflected off, what we see is the complementary color of the light that's being absorbed. So what I mean is like, say you have an orange. So an orange is the color orange. And that's because it actually absorbs blue light the most. But because it absorbs blue light the most, we can subtract blue light from white light and we get orange, which is the complementary color of blue. So you can just like look at a complementary color wheel, but just as a rule of thumb, just know that blue and orange are complementary colors, red and green are complementary, and purple and yellow are complementary. So just keep that in mind because that's just like an important thing to know about color processing and that it's subtractive, it's not additive. Okay, and the rest of this is just like a summary. Oh, one thing is that transition metals form hydration complexes with water. It's because like transition metals can have multiple oxidation states. So like for example, manganese has like manganese 2 plus, manganese 4 plus, manganese 5 plus, manganese 7 plus. And so these complex ions can form like complexes with water and other like non-metals in liquid states. And so they have like variable solubilities because of that. And so that is all for chapter 2. So chapter 3 has some high yield sections. And it is really important for the next chapters after chapter 3. Okay, so I think this is all stuff that you guys know. Bonding is just interactions between valence electrons, octet rule. Everybody learns that in chemistry. And so the octet rule is basically going to be true almost all the time in MCAT chemistry because it's just that carbon, nitrogen, oxygen, fluorine, sodium, and magnesium, which are the most common elements that you'll get in the human body and what you'll get on the MCAT, all follow the octet rule. However, it is important to keep in mind that there's actually many elements. Actually, there's more elements that don't follow the octet rule that do follow it, than do follow it. So it is important to keep these in mind because the MCAT like might trip you up on these. And so just keep in mind that there's some elements that have incomplete octets like hydrogen, helium, lithium, beryllium, and boron. Especially boron, because I have actually had some questions like where they have like boron, they have elements of boron in it. And so like you can only make 3 bonds with boron. You can't make 4. So just keep that in mind. The expanded octet is actually period 3 or greater, and that is because these elements have D shells. And so if they have D shells, then they can use those for bonding. And then there's also molecules with odd numbers of valence, so you can't get like 8 electrons. Like one example would be like nitrous oxide, so NO. So so nitrogen has like 5 valence, and then oxygen has 6, so that's 11. So if you try to like do a bond with that, then there's like no way you can get 8. Okay, so we'll talk more about ionic and covalent bonds, but just know that ionic bonds are almost always between metals and nonmetals, and covalent bonds are just electron pairs shared between 2 atoms, and they're almost always nonmetals. And the degree of sharing depends on polarity, and we'll be talking a lot about this in this chapter. Okay, so ionic bonds, as I was saying, are just like metal plus nonmetal. Like more generally, it's an anion plus a cation. So chloride is an anion, and sodium is a cation. So if you combine those, we get NaCl, which is table salt. And the ionic bonds are extremely strong. And because they're extremely strong, they take a lot of like energy to melt or boil, which is why they have high melting points and boiling points. And they're soluble in polar solvents. We'll talk more about what polar is soon. So, but polar solvents just mean like water or like ethanol, for example. And so these dissolve very well in those. And they're good conductors because the electrons are actually free to move in ionic bonds. And so because they're very, very movable, that's why like they're good conductors of electricity and heat. And ionic bonds are in like a crystalline lattice to maximize attraction between the positive and negative charges. And so just like imagine like plus, minus, plus, minus, plus, minus, and then imagine it as like a 3D cube, for example, or like whatever shape this bond will be in. And so covalent bonds are what's like actually like most important for the MCAT. And so covalent bonds have attractions between shared electrons and the positive nuclei. So they have weaker intermolecular forces, and so that's why they have a low melting point and boiling point. So they're just like weaker than ionic bonds. And because like the electrons aren't free to move in these bonds, they're poor conductors of heat and electricity. Bond length is the average distance between nuclei. So if there's like more shared pairs, there's a shorter length. Like you can just imagine this as like if there's more shared pairs, there's like more attraction. And because there's more attraction, they want to like get closer to each other. And so that's why there's a shorter length between them. Bond energy is the energy required to break a bond. And so you can just think of this as like, if there's more shared pairs, there's greater energy. And so like what it means by more shared pairs is just like single versus double versus triple bond. And so a triple bond is like the hardest to break, so it has the highest energy. And a single bond is the easiest to break, so it has the lowest energy. Polarity is like the difference in electronegativity. So if like one element is more electronegative, then just remember like electronegativity just means that like the element like attracts is more attractive. Like there's more protons in the nucleus, so it's more attractive. And so it attracts electrons more. So it has more electron density than the less electronegative element. Another point, yeah. So polar versus nonpolar bonds. So polar bonds would be like when one element is much more electronegative than the other. And nonpolar bonds are like when elements are like really close in their electronegativities. So on the MCAT, like I don't think we get like electronegativities on the periodic table, but there's like some general trends. Like fluorine is the most electronegative element, then it goes, so it's like fluorine and then there's oxygen, and then there's nitrogen, and then there's carbon. So carbon is way less electronegative than fluorine, for example. The only true nonpolar bonds are the diatomic atoms. I would recommend like memorizing these. These aren't like too hard to memorize because they're like really close to each other, and most of them are halogens. So it's just the halogens plus oxygen and nitrogen. But like we also consider like electronegativities that are really close to each other to be nonpolar as well. So these are just like the ratings. Like the chances are that we probably won't need to know like these exact numbers for the MCAT, but just like keep these in mind. Just like less than 0.5 electronegativity difference, that would be nonpolar. And then more than that, that would be polar. And almost always, if it's a metal and a non-metal, it's going to be ionic. And then dipole moments is just P is the dipole moment equals to the magnitude of charge times the displacement vector. This equation isn't like super important, but like I think it's like pretty intuitive. And so if it's like, if it has more charge and the displacement vector is bigger, then it's going to be a stronger dipole. And oh, sorry, dipoles are just, yeah, so dipoles are basically just like the difference in electronegativity between the atoms in the covalent bond. So just like, for example, a carbon-oxygen bond. So oxygen is much more electronegative than carbon. So the dipole moment vector would look like this. So it's like really intuitive because you just put like a positive charge on like one end, then it points toward the more electronegative atom. So yeah, that's just what it is. And you can find the magnitude of the dipole moment using that equation. Okay, so these problems should not take long at all. So I'll just give like 30 seconds to do them. So these are the answers. So lithium is a metal, chlorine is a nonmetal, so it's going to be ionic. Both carbon and hydrogen are nonmetals, so it will be covalent. Carbon and chlorine are very, very polar because chlorine is a very electronegative atom. And carbon and oxygen will also be polar because the difference in electronegativity is more than 0.5. Just like remember that carbon and oxygen will always be polar. Carbon and a halogen will always be polar because those are like the most common bonds that you're going to see on the MCAT. So more about covalent bonds. So not much about coordinate covalent bonds, but these are just like acid-base reactions. So like a Lewis acid is like an atom that can, or a compound that wants to accept a lone pair. And then a Lewis base is an atom or like a compound that has like a lone pair available. And so that's basically when that base attacks the acid, it creates a coordinate covalent bond. And so this is really only like important just to understand the mechanism of this reaction, because like once this bond forms, there's like no difference with like a standard covalent bond. Like you can just treat it as like a regular covalent bond. Lewis structures are super important. I think you guys probably know how to do these, but just as a review, you always like want to draw like Lewis structures in arrangements that minimize formal charge. We'll talk more about formal charge on the next slide because, but just remember that the less charge that is on the atom, the more stable it is. And so when you draw Lewis structures, just draw out the backbone with the least electronegative atom at the center. And then count out all the valence electrons in the compound, and then when you draw out the structure, the number of valence in the compound should equal the valence of all the atoms. Then you can draw single bonds with electron pairs or lines. You can draw complete octets, and then after that, draw complete octets of the non-center atoms, and then you can put the remaining electrons in the center atoms. If it's less than an octet, then chances are that there's a double or triple bond in there somewhere. So that is what happened here. So in the first compound, nitrogen is the least electronegative element, so it's in the center. And then this is just the diatomic oxygen here, and then it's double bond because like if you drew this out, you would find that there's like one electron missing in each. Okay. So this also like shouldn't take like too long. Yeah. So I'll just give like a minute to do this. Okay, so these are just the answers. So Lewis structures are like incredibly important. Like, maybe not like, you don't have to like draw like all of the electrons out. Like usually when you're drawing Lewis structures, just like know that they're there, like all the lone pairs are there. But what's important is just like knowing like what a Lewis structure is and what they mean. Just some standard things. Carbon always has 4 bonds, like always. It never has 5 bonds. It just cannot do that. So if you're ever like working on a problem and you see that carbon has like 5 bonds, just like know that you did something wrong there, or that you need to like break a bond with something to make sure that carbon has 4 bonds. There is like there are like carbocations that do happen as reaction intermediates. That's like more organic chemistry. We might talk about it in general chemistry. I'm not completely sure. But once we get to the organic chemistry review sessions, we will talk a lot about carbocations or carbons with a positive charge. And so if you did the cyanide Lewis structure, you would see that there's a triple bond there. So yeah, so and then methane is just really standard. Like hydrogen has two valence electrons, and so you can always only make one bond. Okay, so formal charge. Formal charge is like pretty important just as like a concept. If you ever need to like check your work, like just like looking at the formal charge is helpful. Formal charge is like especially important when drawing resonance structures. So resonance structures are like way more important in organic chemistry, but they're still like really applicable to general chemistry as well. So we'll talk a little bit more about it. So formal charge is like the normal number of electrons. There should be electrons in the valence shell. I'll change that. It's the normal number of electrons in the valence shell versus the number of non-bonding electrons, minus 1/2 the number of bonding electrons. Because like remember, like when a bond has two electrons, but like you're basically assuming in a formal charge equation that like the electrons are distributed equally between the two atoms in the bond. So like each atom only gets one electron, and that's all that means. Resonance structures are like super important. Like they're so important for the MCAT. So this resonance structures basically have like the same atom connectivity, but like different electron distribution. And so the actual structure is a hybrid between different structures. So it's a resonance hybrid. So I guess you guys have probably like drawn resonance hybrids before, or like resonance structures before, but just like keep in mind that like the true structure is not like switching between resonance forms. It's just like one structure. It's the resonance hybrid. But like we have no way to draw that, so we have to draw both structures. But just remember that like the true structure is like in between those structures. And so like as an example, like say one resonance structure has like a lone pair on an oxygen, but the next resonance structure has like a double bond between the carbon and the oxygen. And so the true bond would actually be a 1.5 bond. So it'd be in between a single bond and a double bond. And so that has like massive implications on like reaction mechanisms and like the properties of the compound. And so we'll talk more about that like in later chapters. Um, when you're looking at resonance structures, the more stable structure is the major contributor, while others are minor contributors. So that just means that like if one structure is more stable and then another structure is less stable, the more stable structure like maybe gives like 75% to the resonance hybrid, while the other ones only give like 25%. And so you can tell whether a structure is more stable if it has like less formal charge, less separation between opposite charges, and the negative charges are on more electronegative atoms. So less formal charge would be like if you calculate the formal charge of each element, and you can see that some elements will have like like some resonance structures will have like more elements with charges. And so when like looking into resonance structures, you would pick the one with like less charges on each element. And then less separation between opposite charges, like if there's a plus formal charge and a minus formal charge, then like if they're close together, that's more stable than if they were far apart. And then the negative charges on more electronegative atoms, like if there's a negative charge on like oxygen, that's like more stable than if it was on carbon, for example. And it's really important to keep exceptions to the octet rule in mind when calculating formal charge. Like for example, boron has like 6 valence electrons um, that are like available to bond, so it can only do like 3 bonds. So it's important to keep that in mind when like calculating formal charge. Okay, so I'll just give you guys a minute to do this. These are like these should be like pretty simple. Okay, I think that's about a minute. Okay, so if you calculate the formal charges of like each atom, you can see that carbon has 4 like electrons normally in its valence shell, and it has 0 non-bonding electrons. Like if you drew out the structure, just try it out. Let me see if I can find my pen. Okay. So carbon chloride would look like this. Sorry, this is so ugly. It's okay. Um, okay, so the carbon chloride looks like this. So carbon has all of its valence electrons participating in bonds, all 4 of them. And so there's no non-bonding electrons. And then it has 8 electrons involved in bonds. But it only has like 4 to itself. And so this is just 4 minus 0 minus 4, that's 0. So carbon has like no formal charge. And then chlorine has 7 valence electrons generally. It has, it also has 7 non-bonding electrons, or like 6 non-bonding electrons, I'm sorry. And then 1 electron to itself in the bond. And so this is also 0. So the total formal charge for this molecule is 0. The resonance forms of benzene are like pretty simple. There's only like 2. And they're actually both equal contributors to the hybrid. And so you can kind of see that the hybrid is just like right in between both of these resonance forms. Yeah, so benzene is an aromatic compound. It just means it like smells really good. It's really important in organic chemistry especially. Please remember benzene. And please remember organic compounds because aromatic compounds because aromatic chemistry is a major part of MCAT organic chemistry. Okay, so I think the last part of covalent bonds is the VSEPR, or VESPR is just what I call it, theory. And that's just like how 3D arrangements of the atoms are made. Like Lewis structures, like this isn't really how it looks like in real life. But this theory like gives like 3D arrangements, like what they would actually be, like if we could actually see the molecules in real life. If you have like a molecule building kit, you can like make these and it would be like really obvious to you. But just like remember that electrons always want to be as far from each other as possible, and this is just because of simple laws of repulsion. Negative charges never want to be near each other. And so this is how they would arrange themselves. I would actually say that you guys should memorize these because they are like really important. But like I think like if you know that like electrons want to get away from each other as much as possible, like some of these are like pretty intuitive. Like linear is like the farthest these 2 electrons can possibly get from each other. Trigonal planar, that's also as far as they could get. Tetrahedral and trigonal bipyramidal and octahedral are perhaps like less intuitive, but like if you just like look carefully at the structures, like you can see like this is about as far as they can get from each other. And so these are like the standard bond angles. Definitely memorize like 180 degrees, 120 degrees, and like 109.5 degrees. The other ones aren't that important. They're good to know, but like the first 3 are like super important, and it's actually because carbon makes like tetrahedral structures because it has 4 bonds, and so most of the reactions that you're going to see will most likely involve carbon. So one important distinction is between electronic geometry, which was this, versus molecular geometry. So electronic geometry includes like both bonding electrons and lone pairs, while molecular only includes like real atoms that are bonded. Like for example, if you look at tetrahedral in electronic geometry, then say like the bottom atoms that are attached to like what we can say is carbon are real atoms, and then the top is just like a lone pair, and that would be the electronic geometry. However, if there was only like 3 atoms attached to like the central atom, in molecular geometry would actually be trigonal planar. And so we should just like keep that in mind. Yeah, so the coordination number is important for molecular geometry, just like the number of atoms. Like it's really simple. So one other thing that is important is polarity. And it's that polar bonds may actually be polar or nonpolar. Nonpolar bonds are always nonpolar. And that's because like the molecular geometry could actually cancel out the dipole. Like just as an example, say I drew, so carbon, and these are all chlorines. I wish I was better at like drawing on here. It's okay, whatever. Okay. And then it would be like this because chlorine is like way more electronegative. This would all be like that. And so like once you draw it out, like you can see that like these cancel each other out and these cancel each other out. So this compound is actually nonpolar. However, like other compounds like water, for example, are actually polar. And it's because like if we draw water, we can draw like H, O, H. Oh God. Okay, just imagine that's a bond. So it's because it's like this. And see, so like that doesn't cancel out. And so water actually is polar. So yeah, that's like a pretty important concept to keep in mind.
Just a minute, sorry. The CCl4, like in the previous question, you had said that it was polar, but now you're saying it's actually non-polar.
Oh, you here?
No, no, no. Like when we had to the
Oh,
CO
yeah.
and
Yeah, so like that bond was polar. So like um if you okay, let me just go back to that question really quick. Okay.
yeah, this one, Lewis struck.
Not this one.
No, this
Okay,
one.
it's this one. So
Mm-hmm.
this bond is polar. Like if you draw it, so CL. So I'm sorry, it's so ugly. Okay, so this bond is polar, but this molecule is not polar.
Oh, okay, okay.
Yeah.
And what? Sorry, what is this cross like a plus sign you're drawing again?
Oh, okay. So this is the dipole moment. Oh
Dipole
God.
moment. Okay.
Yeah. So this is carbon. This is chlorine. And so chlorine is more electronegative. And so we would put the arrow toward the more electronegative atom. And to make it obvious which one is more positive, you can just do that. So this is a plus sign for the more positive atom.
Oh, okay, got it.
Yeah,
Thank you.
no problem. Yeah, I mean, it's kind of weird, but like sometimes you have to like differentiate between like bonds and between molecules. So like even if like a bond might be polar, the molecule itself might not be polar because of molecular geometry. Okay. Okay. Okay, and so molecular orbitals, like this isn't like super important. But like you just like when you make a bond, you're combining like atom orbitals. Like that's what a bond is. Like you're combining the orbitals that the valence electrons are in. So you don't like bonding versus antibonding isn't like important. Just like know what that is, but like it's not like really important. But like what is important is knowing what sigma bonds and pi bonds are. So sigma bonds are like head-to-head overlap. Like what I mean by that is like say these are like two electron clouds and they're overlapping, and that's a sigma bond. But pi bonds are like parallel electron densities. And so say like these are two electron densities and these are like bonded together, but they don't like overlap. And that's basically the difference between the two bonds. What else is important is that sigma bonds are flexible. And so sigma bonds are single bonds. So for example, like if I did like this, for example, oh my God. So basically like they can turn. Like they're really flexible, like they can bend or change shape. I'm having a really hard time drawing, but whatever. Let's see if I can draw pi bonds. Okay, but pi bonds are like the additional bonds. Like this is a pi bond. If I put like a triple bond, that would also be a pi bond. So the first bond is always a sigma bond, and then the bonds on top of that, if it's a double or triple bond, are going to be pi bonds. So a double bond has one sigma bond, one pi bond, and a triple bond has one sigma bond and two pi bonds. So what's important about these are that they can't rotate. Like if there's a pi bond, it can't rotate. So what if I had like this molecule? Okay. Okay, so these atoms are like fixed in place around this molecule. Like they can't move anymore. However, if it was like a sigma bond and we had like a similar molecule, just like for 1 second, just like ignore that carbons. Oh, actually, no, we don't need to do that. We can just do this. Okay, and next time I'm gonna try to like do this on my iPad so I can actually draw things. But yeah, so this is the same thing as like this. Okay, so you can kind of see that like on the left side, like the two atoms could switch places, and they could do that because sigma bonds are flexible. But like on the bottom, these cannot switch places, and it's because pi bonds are rigid. And like this is actually really important or in both general and organic chemistry. Like when you are on the NMR spectroscopy part, like I know that's like really far ahead in the organic chemistry book, but if you guys have finished that book, then like you'll know that like the rigidity of bonds is like really important to spectrums of elements and also like in reactions. Okay. Okay. So that's basically all you had to know. And then the last part of this chapter is just intermolecular forces. So these are also like pretty intuitive, I think. And so these are just interactions between atoms. So like intermolecular, between molecules. So London dispersion forces are the weakest, and they're basically due to like dipole moments that are short-lived. So like say you have a nonpolar bond and like on average the electrons are shared equally. However, electrons aren't static. They're like dynamic. They're like constantly moving. And because they're constantly moving, there's going to be like a few milliseconds here and there where like one atom is like more electronegative or like less electronegative. And that's what London dispersion forces are. If like by chance these like short-lived dipole moments meet like another molecule in which the electrons are moving and they also have a short-lived dipole moment, like they're going to either attract or repel each other. And so, because it's such a weak force, it only works like if the molecules are in close proximity. But they are greater in large molecules because there's like more electrons that move around. Yeah. And then the second one, which is moderate in strength, is just dipole-dipole interactions, and this is in like polar molecules. And so if you just like imagine this, like if you have a polar molecule, then like it's in like a solid or a liquid phase, then it's going to arrange itself so that it's in like it's like in the most stable state possible. And the most stable state possible is like when it's with other atoms like it's attracted to. So like if I draw this out, like this is really bad, but okay. Okay. This is plus, and this is minus. And so this would be minus, that would be plus. This would be plus, and this would be minus. Just imagine like these are better, but like see, like those. Those would basically be the dipole-dipole interactions. And the reason that they don't happen in gaseous states is because gases like are really like spread apart, and so like the molecules are like always moving, and so they can never like stay in one place long enough to have like dipole-dipole interactions. And hydrogen bonds are super important. Like you will 100% see like many questions on hydrogen bonds on the MCAT. And so like this is just like a really quick overview of what hydrogen bonds are, but we'll go into so much more detail about these and they're so important. So just like know like right now like what they are. And so just conceptually, a hydrogen bond is when a hydrogen is like bonded to an electronegative atom and it's these three, it's nitrogen, oxygen, or fluorine. And so basically these atoms are like so electronegative that they basically steal all of the electron density away from hydrogen. And so hydrogen basically acts like a proton then. And because it has like no electron density, that means like it's like super attractive to electronegative atoms on other molecules. And so basically this is a very strong, it's like the strongest force, the strongest intermolecular force. And it's the reason why like molecules that have hydrogen bonds have like a high boiling point. And so just as an example, like if I draw this out, like water is probably like the most famous example of like hydrogen bonds. And if like water did not have hydrogen bonds, like we would not be here. We would probably not have anything if there was no hydrogen bonds. Okay, so these are two water molecules, very poorly drawn. Um, so on this water molecule, the oxygen is super electronegative. Let me actually do this in a different color. So the oxygen is like very electronegative. It's like taking all of the electron density away from the hydrogens. And this oxygen is very electronegative because it has like all of the electron density. And so there's a hydrogen bond interaction that happens between the hydrogen and the oxygen. And so there's basically kind of like a bond here. I mean, it's like not really a bond because bonds are either covalent or ionic, but like it's the strongest intermolecular interaction. So just like know what these are like right now because you're going to be using them a lot. Like even in like biochemistry or biology, like you'll see like hydrogen bonds being mentioned.
So if hydrogen is bonded to a carbon, does that count as a hydrogen bond?
No, it doesn't. Carbon is not electronegative enough. It's only like these three. It's only nitrogen, oxygen, and fluorine.
How about, sorry, I know they're more electronegative.
Yeah, but like those bonds aren't like very like common. So on the MCAT, like what you're going to be seeing is like these three atoms.
Okay, just
Yeah. So I mean, I think like if you did
how
have the,
about
you're
chlorine
right.
and hydrogen?
Sorry?
Chlorine and a hydrogen.
Yeah, so you can have like fluorine and hydrogen bonded.
No,
Like,
like chlorine.
oh, chlorine.
Hmm.
Um, I think you can definitely have chlorine. Yeah, I mean, you would, chlorine and hydrogen is like HCl, it's an acid. But like that interaction is like, it's going to be like acid-base chemistry. And so it's like not important for this. Like hydrogen and chlorine is HCl, which is like a strong acid. And so like when that happens, like the most important interactions are going to be like acid-base chemistry, which is like a later chapter. So it's like not that applicable here.
Okay.
Yeah. But like based on this book, they just like told us to keep like hydrogen bonded to nitrogen, oxygen, and fluorine in mind for hydrogen bonding.
Okay. And I had one question. I know like electronegativity increases from left to right and it
Yes.
decreases down the group, right?
Yeah.
So does that mean that nitrogen is more electronegative than chlorine?
Nitrogen should be less electronegative. I think I should probably like check to make sure, but I'm pretty sure it is less electronegative than chlorine because like if you draw it out,
Mm-hmm.
like say I drew this, like the periodic table is like nitrogen, oxygen, fluorine, and
Mm-hmm.
then chlorine is right here. So because it's like closer to fluorine, it should be like more electronegative than nitrogen, which is all the way over here.
Okay. Thank you.
Yeah, and just like remember that it's because that chlorine, like here in the halogens have more protons, and so that they have more attractive force.
So the more protons that an element has, the more electronegative it is.
Yes. But like electronegativity is like really the most important for like basically these elements here. Like this is what you're going to see on the MCAT. So carbon is not very electronegative at all. Nitrogen is pretty electronegative. Oxygen, fluorine, chlorine, bromine. It's like these elements that like it's most important for. Sulfur, yeah, because these are the elements that we're most likely going to see on the MCAT. And if you like look at the periodic table, like obviously like the least electronegative elements would be like the metals. But like at that point, like you know, it's if it's a metal and a non-metal, it's going to be an ionic bond because like it's such a huge difference in electronegativity. Okay. So I think that's it. I think we've covered everything in all three of these chapters. So unfortunately, I don't think we have time to cover like chapter 4 today because like we're almost already at like 7. But like so you guys are like free to leave if you want, or we can like just talk more about like any questions you guys may have. Okay. Yeah. So oh, one question I have is that like um I will upload this into the Google Drive. Does like everybody have like does everybody have like access to the Google Drive?
With the MCAT 2020 Google Drive?
Yes.
Yeah, I think I have it on my Google Drive already.
Okay, awesome. Yeah, in case it isn't there, like I can just like post another link. But yeah, so these chapters like aren't like really hard or anything. Like they're really important like foundationally, but just like knowing the concept should be enough. Like and like for most of the MCAT like problems, like you don't need to know like these equations. Just like know the proportions and you should be like okay like 99% of the time. And so, yeah, I guess that's all I really had to say. But yeah, I will definitely post like another link like in both the in like the group chats, and I will upload this video onto the Google Drive. Also, I had some questions like what I can improve because I just like added problems in. Like, do you guys think this was helpful, or do you think like the problems aren't necessary and like maybe we should just like do like one single MCAT problem at the end, like from Khan Academy or something?
No, I think we can, if you want to add Khan Academy into it, that's fine. But like just to, because sometimes I'm like, okay, I don't understand what this means until like it presents itself in a problem, and then you're like, okay, this is how I'm supposed to apply this knowledge, sort of.
Okay, yeah, that was like my thought process too. Like when I read this stuff, like I can get the concepts, but I like have no idea what equations mean until like I see them in action. But yeah, thank you. Is there also anything else that you want me to like include on the slides? I just like added like summaries of like each chapter, like each section, plus like one problem. Is there anything else that I should be including, like, or anything else that you think guys think would be better to like improve the sessions?
So are you saying that equations we don't have to memorize them? You're saying?
Oh no, I'm saying like these are summaries of like each chapter plus like equations that Kaplan recommends we memorize. So like the highlighted equations
Okay.
are stuff that we should know or like at least like know the proportions to. Um, yeah, so what I was asking, like, is there anything else like I should be adding or should be taking away to like be more effective?
Maybe like if it's not too much trouble, like all the equations that we like talked about, like maybe if you had a slide, like a summary slide at the end, like with all those
Oh, okay.
equations that we need. I think
Okay.
that'd be pretty helpful. Also, I don't know, like maybe like an example or like just one or two like example like MCAT questions, but like
Oh,
maybe
okay. Okay.
yeah. But I think maybe the equations would be pretty helpful
Okay,
as
yeah. I'll add a
well.
summary slide at the end then, and then with all the equations. Okay, yeah, that sounds really great. Thank you so much, guys.
Thank you.
All right.
No problem. Thank you.